Hello, everybody. Thank you for attending. In the interest of time, I'm going to start the introduction so that we can keep to the schedule. So hopefully you are seeing the screen now. So yeah, welcome and thank you for attending. I am William Smith. I'm a research scientist at the FDA Center for Drug Evaluation and Research. It is my privilege to be hosting this meeting on the behalf of the National Nanotechnology Initiative. The NNI is a U.S. government R&D initiative consisting of over 20 federal agencies and departments who work together to achieve a vision of the future in which the ability to understand and control matter at the nanoscale leads to ongoing revolutions in technology and industry that benefit society. I would like to take this opportunity to inform you, that next week is National Nanotechnology Day. October 9th, National Nanotechnology Day is an annual event where we have community-led events and activities to raise awareness for nanotechnology. Of course, October 9th, or 10-9, pays homage to the nanometer scale, so 10 to the -9. If you want to join in the celebration or participate, you can do so simply by just, posting something about nanotechnology on social media using the hashtag National Nano Day, or organize your own internal and external events and activities. And you can find some examples of some ideas there at nano.gov. So today we're going to be continuing our nanometrology webinar series. The aim of the nanometrology webinar series is to highlight the challenges, advancements, and importance of measurement technologies that help researchers probe nanomaterials in order to spur innovation, generate improved data, and experimental design. This series began earlier this year with a focus on recent advances and current challenges in synthesis, characterization, and application of nanoparticles in medicine, food and agriculture, and electronics. If you're interested in that, you can go and see all of our recordings on nano.gov. So today's webinar is Nanometrology for Continuous and Automated Manufacturing. We're going to talk about some of the challenges related to inline and outline measurement in continuous systems, as well as measurements that are made in automated systems. There is another webinar on the slate for November 1st, and this will be nanometrology involving big data, AI, and modeling. So if you have the interest, please register and join us on November 1st at 12 p.m. So let me introduce some of our speakers today. So we are really lucky to have with us today this group of speakers. First up is Dr. Suji Park. Dr. Park is a staff scientist at the Center for Functional Nanomaterials at Brookhaven National Lab and has expertise in synchrotron X-ray microscopy, neutron imaging, and ultrafast X-ray or electron diffraction, excuse me. Her project centers on the development of the Quantum Material Press, or QPress. It's a cluster tool designed for high throughput production and characterization of heterostructured 2D materials. The primary objective of the QPress is to establish a reliable and efficient method for fabricating 2D materials, which will benefit the rest of the 2D research community. This process has been fully automated and optimized to ensure both high yield and high reproducibility for the production of these high quality 2D materials through the application of things like in situ and inline measurements. So thank you for joining us, Dr. Park. Next up, we will have Dr. Yevgeny Raitzys. He is an expert in experimental plasma physics. He has an extensive publication record with over 200 publications in physics of plasma thrusters, plasma surface interactions, plasma-based synthesis and production of nanomaterials. Since 1998, he has been with the U.S. Department of Energy at the Princeton Plasma Physics Laboratory, where he leads research on low-temperature plasma with applications in plasma propulsion and synthesis of nanomaterials. He is also the director of the DOE-funded Princeton Collaborative Low Temperature Plasma Research Facility. And among many other honors in 2019, he received the PPPL's Call Foundation Prize for Excellence in Plasma Physics and Research and Technology Development. So thank you for joining us, Dr. Reitzes. And lastly, we have Dr. Milad Abulhassani. He is an Alcoa professor and university faculty scholar in the Department of Chemical and Biomolecular Engineering at North Carolina State University. He received his BS and MS degrees in mechanical engineering from Sharif University of Technology and the University of British Columbia, respectively, and then obtained his PhD from the University of Toronto in the Department of Mechanical and Industrial Engineering. Before joining NC State, though, he was a postdoctoral fellow in the Department of Chemical Engineering at MIT. Dr. Abulhassani leads a diverse research group that studies self-driving labs tailored towards accelerated discovery, development, and manufacturing of advanced functional materials and molecules using fluidic microprocessors. Really cool. So thank you for joining us as well. Some quick housekeeping stuff. The meeting is recorded and will be posted later if you have to leave unexpectedly or want to share with others. And please use the Q&A chat to ask questions. We have allotted a brief period after each speaker to address questions from the audience. So thank you so much for joining us. And with that, I would like to ask Dr. Park to share her screen and begin the presentation. Thank you, everybody.
Okay, thank you so much for the warm introduction. And thank you for inviting me to this webinar series, and it's my honor. Hello, I'm Suji Park, a staff scientist at CFN. And today I'm going to talk about a new facility at CFN dedicated to 2D materials fabrication. My focus today will be what's the 2D materials and why they are important, and what is quantum material press and why we made it, and some characterization techniques for QPress system. Okay. First, I'd like to provide a brief introduction to CFN. So CFN is one of the 5 nanoscience research centers in the United States, located on Long Island, New York State. So our mission is to enable researchers to conduct their every aspects of their work related to nanomaterials under one roof. Users can submit proposals to access our resources for theoretical predictions or material synthesis or characterization at free of charge. So please check out our website here, our website for more information. Okay, now without further ado, let's dive into the main topic. So interestingly, the most well-known 2D material is something that we can find everyday life, which is graphite. So we can write and draw lines with pencils because the graphite has a slippery layered structure made up of graphene sheets. The layers are held together by van der Waals force, which is very weak interaction. So this interaction allows us to isolate each layers with relatively little effort. So in 2004, these two great scientists, Dr. Geim and Novoselov, they found a very easy way to isolate graphene sheets from graphite using a piece of Scotch tape. And 2D materials has been paid tremendous attention since then because it has a lot of potential in a wide range of applications. The technique is very simple. First, we place a bulk crystal on a piece of tape and distribute along, folding and unfolding process. And press gently on silicon oxide wafer and peel off. Then bring it to the microscope and start searching. And repeat this process until we find a good flake. So this technique is very handy, and it produces clean flakes that maintain their crystallinity, resulting in significantly fewer defects. Therefore, this method produces a highest quality 2D materials among other production methods still, and used in many cutting-edge researches and prototypes in many, many applications. So exfoliated 2D flakes allow us to create a new heterostructure by stacking them into different sequence and orders and orientations. There are two main approaches for stacking this heterostructure, wet and dry transfer. So wet transfer was developed first, but it leaves some residues and it introduces chemicals every step. So people use the dry transfer most. It uses sticky polymer like PDMS or other sticky layer to pick up and stack layers from top to bottom. The only topmost layer is exposed by polymer, so it can maintain the cleanness of the other layers. More interesting and exciting research started in 2018, led by a research group at MIT. So they discovered a superconductivity in twisted bilayer graphene at magic angle, which is 1.1 degrees. When two graphene layers stack together at certain twist angle, it forms a Mora pattern and a superlattice structure. So it tweaks or modifies the electric band structure, and we can see the unusual behavior, including superconductivity. So this is very exciting opportunity for us to investigate a new whole field using 2D materials. So as you've seen, 2D materials research holds huge potential, and the field has grown rapidly, and new 2D materials beyond graphene has been found for 20 years. However, despite this progress, the production method for 2D materials have remained manual and labor intensive. While this method served well this field for 2 decades, is now a bottleneck that we need to overcome to go further. So that's why we developed QPress SCFN. This is the automated 2D fabrication and characterization facility designed to accelerate the advancement of 2D material research. Okay, this is the footprint of QPress. So we have vacuum side and glue box, inner gas glue box side. So in vacuum side, we have sample libraries so that we can store up to 100 wafers. And we have E-beam evaporator to deposit some metal layer, and annealing and plasma chamber to clean flakes or do some surface treatment. In glue box, we have 3 custom modules, so home-built modules for the fabrication of 2D flakes. So this is what happened in the glue box. So we use robot transfer system so that we can load and unload 3-inch wafer. And this is the exfoliation machine called exfoliator. And then we move the microscope after exfoliation to find flake. And the sticky polymer stacking method. So stacker can help us to fabricate a new heterostructure. Okay, thank you for watching. Okay, so to design this kind of machine, we must understand the fundamental mechanism and identify which parameters matter, in what range, and how they interact. So let's start by clarifying 2D exfoliation. So in tape exfoliation system, it consists of four layers: tape backing and pressure sensitive adhesive layer, and 2D crystals and substrate. Actually, there are four different failure modes depending on the location of the weakest interaction between layers. So what we expect for successful exfoliation is the microcleavage happening in this interlayer site of 2D crystal. However, the other three is also useful for dry transfer because it's pick up and drop off motion. So it's actually the competition between viscoelastic PSA layer and elastic 2D films. So we need to be able to control these two main parameters. And also we need to understand what peeling is. So peeling equation suggested by the Kandel contains the material property itself, the elastic deformation, and also the peeling force depending on the peeling angle. And actually the adhesion in elastic film is depending on the peeling speed as well. So we need to consider all these separate parameters and put it into a new one machine. So we took into account all parameters, and here is the exfoliator. We use roller assembly, so we have press roller and all these tape reels and motor stages to control the rolling and peeling conditions, including rolling pressure, speed, and temperature, and also peeling conditions, the peeling force and speed and angle. We developed recipes for common 2D materials like graphene, HBN, or some general TMD materials. And these are not like perfectly optimized yet, but it does its job pretty well. So this is the robotic exfoliation process. So it consists of 2 cycles of exfoliation. The first step is using the tape and transfer it to the tape of exfoliator. So we prepare a crystal with the tape and roll and peel. Then the sum of crystals are transferred onto the exfoliator. And then we move this area under the press roller and switch the substrate to the silicon. And then we run the rolling and peeling conditions again with different parameters. Okay, so this process is written in the recipe so that we can produce consistently the similar quality of crystals. Okay, now exfoliation is completed. So after exfoliation, we use optical contrast and color to find and estimate the thickness and later size and shape. For thin flakes, the light interaction with this flake and oxide layer generates some certain contrast and color. Here is the image of graphene on 90 nanometer oxide wafer. So this part is monolayer and this 5 layer and 6 layers. As you can see, the contrast increases proportionally with the number of layers. And this optical method is actually better than AFM, which has very thin steps here. For thick HBN, it generates like these beautiful colors. So we can estimate the rough thickness by this color. The oxide layer thickness is also important. So this is 90 nanometer silicon oxide, and this is 300 nanometer silicon oxide, and it generates different colors. So we choose different oxide thickness for different materials to maximize the visibility. And also we can use the separate channels, RGB channels, to go further. Sometimes certain channel displays much better contrast, so we can actively use these functions. The cataloger we call is the automated flake detection system using these optical images. So we use machine learning, the deep neural network technique, to find the thin layers. So first we scan the entire 3-inch wafer and make this map, and each images will be fed to this algorithm, and this neural network machine learning code will find these thin flakes for us. This is very powerful and is very helpful. However, it's hard to find like large data set of reference. In particular, some exotic materials or new material, it has its limitations on that. So there's another approach using the RGB color. So in this approach, we use RGB channel, and it generates clusters of each layers in the RGB space. Then these are the fingerprints of each layer. And this method does not require large data set. So it is useful for some rare materials. However, because it uses RGB and the imaging system, so different imaging system can produce some different information. So we believe that combining these two approaches, the machine learning, the neural network, and its heuristic technique, will be a more complementary and robust detection system. So we are pursuing these two directions. Cataloger also incorporates some other characterization techniques. So first we have AFM. So some flakes are actually invisible or hard to see, or some hidden steps on the surface of flakes, or some residues could be detected by AFM. Or if we are not sure the contrast of the new material, then we can confirm the thickness with the AFM. Also, Raman is very useful tool and very quick and easy. And some material has this fingerprint, so the peak position or the ratio of different peaks displays the thickness and or some strains, or some techniques actually can verify the crystal orientation as well. Another useful technique is the photoluminescence. It's not every single material can do it, but some TMD material shows significant change depending on the thickness. So we can use the PL to identify material, and also some applications on using defect engineering. Fortunately, we don't have a tool to find directional information, which is critical for twisted structure fabrication. So one of the opportunity that we are planning to add is the polarized secondary harmonic generation. So this is just for the non-center symmetric materials, but is very useful in many cases. As you can see in this image, this SHG signal is shows the direction of armchair direction of MOS2. So we can examine two different flakes or the stacking region which is sensitive to the twisted angle so that we can examine like if the stack is correct, or even before we stack each separate crystal flakes, we can measure the angle and then stack them into a structure. So we are planning to add this function to the cataloger in near future. Okay, finally, we are ready to stack. So the catalog flakes are stacked by this motorized stacker. So stacking process requires like sophisticated motion control in stamp and sample. So we employed 6-axis hexapod so that it can make like free motion like a hand. So currently, stacker is fully motorized and the operator should operate it from outside of glue box, but we are trying to make it fully automated using the machine vision as well. Okay, this is a user experiment we did like right after I made this stacker. So this is the real-time cleaning process. So you can see this is the polymer contaminated graphene stacked on HBN. So this line is actually the polymer residue trapped in between and is pushed out by this lamination motion. So in this technique, we found that a certain thermal and mechanical actuation requires to make a clean stack without any polymer residue. So we examined this clean area with Raman. Raman is actually sensitive to the strain, so it can show the rough and clean interface by the peak width. So it shows this clean area by certain like hidden parameter control. Okay, in summary, the QPress is the streamlined 2D material fabrication platform. It uses optical characterization method to combine all together. And we have optical microscope, AFM, Raman, MPL, and we're planning to add SHG in near future. And we keep developing new capabilities to support various 2D material researches. So please be a user. Okay. Okay, I want to thank everyone support this project and all the user groups that I worked with. Hey, I'm ready to get to questions.
Sure, if people have any questions, please put them in the Q&A for us. But I think one, really interesting. Two, I think maybe, and this might be my bias of working with things not so much in the solid state, but you know, typical like if you're using like a confocal or a laser profilometer, you're using a lot of coherent light and usually like, you know, single wavelength. So could you just kind of hop into why you ended up going with white light, or is it you know, a mixture of LEDs or like a broad wavelength, and what was kind of the thought process of using that as your kind of contrasting and methodology?
Okay, so first of all, the white light gives you the RGB channels, so which is the great way and simplest way to identify flake. And because it's unique capability, the RGB channel, the separation of RGB channel and the selectivity of the certain wavelength, that is the first thing we could come up with, the easiest way to verify the flake. And also we are using laser as well. So Raman AFM uses the single wavelength. We are using 532 nanometer laser. So everything is integrated in one body in cataloger. So we are switch the white light and also laser technique as well.
Nice. It looks like we did get a question in here. Besides polarized second harmonic generation, are other techniques to investigate directional properties in twistronics, given its many applications?
Yes, actually, because we don't have SSG in now, the current setup, so there are different techniques outside. So SHG is one thing. We do have one in CFN, or we have electron diffraction so we are next to the NSLS2. So we have a great opportunity to work together. And also recent findings are, the Raman spectroscope, like polarized Raman, and also finds some directional information as well. Yeah, so I think that these are like most people just use like electron diffraction. That's most like confirming technique. Yes. But because we want to make the system in the glow box for the air sensitive materials, so that's why we are considering the optical characterization method to verify the orientation information.
Very nice. It looks like we have time for maybe like one more question, so I'm going to kind of jam these two together. So you did talk about some molybdenum sulfide and mentioned graphene. So this question says, apart from graphene, what other materials are there significant experience with transferring using the press technology? And the second question kind of ties into that, which is there any downtime between preparing samples or flakes of different compositions?
Yes, so the first question, so we are dealing with different kinds of 3D materials, not only graphene. So we've exfoliate and stack graphene and HBN and the common TMD materials or some magnetic materials as well. So for TMDs, the most common is WSC2, MOSC2, or sulfide, or some telluride, which is air sensitive. So for air sensitive magnetic materials and TMDs, QPress is great opportunity to complete this from start to end in the inert gas environment. And we do have a vacuum suitcase so that we can transfer the stack or flake to another vacuum system directly. And the other question was, I
Is
forgot.
there downtime between
Okay.
preparing samples of different compositions?
Yes, because to make a stack, basically you need different kinds of, flakes, right?
Right.
So you need to exfoliate one thing and catalog it, and another thing and catalog it. And after you prepare all the ingredient, you can start the stacking. So if you think that is a downtime, yes, it's downtime.
Sure. So it's like a prep step. You're loading up
Yes,
your magazine to actually load the stacks.
yes.
Well, that was really great. Thank you so much. Very interesting. I think in the interest of time, we're going to move on to Yevgeny. So thank you again so much, and look forward to hearing more about your research in the future. Yevgeny, you can take over.
Thank you. Hello, everyone. Can you see my slides?
Yep, looks good.
Okay. Hello. Yeah, thank you for invitation to give this presentation. My name is Evgeny Raitis. I'm from Princeton Plasma Physics Laboratory at Princeton, which part of the Princeton University, but it's a USDOE laboratory operated by Princeton University. And my talk will be in line characterization of carbon and boron nitride nanotubes during plasma synthesis. Actually, we'll be less talking about tubes themselves, but rather about diagnostics of synthesis in situ. Let me just briefly introduce PPPL. PPPL is a U.S. Department of Science, Department of Energy Office of Science, Fusion Energy Science Office Laboratory. As I mentioned, it's operated by Princeton University. PPPL has three coupled science missions. Develop scientific knowledge and advance engineering to enable fusion, magnetic fusion, to power US and the world. This is our main mission. And on this figure left at the bottom, you can see our National Spherical Torus experiment, which is currently on upgrade to get to advanced regimes. Second mission is advance the science of nanoscale fabrication for industry of the future. And it includes not only nanomaterials, but also microelectronics, nanofabrication. And the third is advanced futures, the scientific understanding of plasmas from nano to astrophysical scales. And then the right figure here, you can see experiments, laboratory astrophysics experiments. This specific experiment will be focused on studies of magnetic reconnection. It's called FLARE, which is soon will be operational. And this is the center where you see PPPL. It's basically 4 miles away from Princeton University in Princeton Township, and this is a lab. It was formed in 1952 by famous astrophysicist Lyman Spitzer, and since then it grew to become national frontier in fusion sciences. In addition to fusion and laboratory astrophysics experiments and sciences, we also have user facility which is focused on providing expertise, research capabilities in experiments, diagnostics, and computational on plasmas which are more in use by day by multiple users, such as it's called low temperature plasma. I will show you later what does it mean, low temperature plasma, but basically from fluorescent light to your plasma reactors in clean rooms and many other applications involve low temperature plasma. And this facility provides service and provide community access to basically when you want to understand what your plasma do for you, and you don't want to use plasma as just a microwave oven in your kitchen, then you're welcome to come to us. And since 2019, our start, we basically have working on more than 100 user projects. And these are examples of diagnostics which we have. It's all in situ diagnostics, although we also have access to material facilities at Princeton University. This is our nano lab, which is qualified to work with nanomaterials. This is a team, and these are plasma sources which we have, and simulations which we do. Of course, these are simulations of plasma, but also we're involved in a plasma surface interactions, both experiments and simulations. And if you're interested, welcome to come. So this is a little bit more about our research on different topics, and you are welcome to visit these websites. Just to give you, because most of you probably solid state physicists or chemists, so just to remind you what is the plasma. It's a fourth state of matter, and this is temperature versus density particles diagram. And so you can see that fusion plasma, which is basically almost like a sun plasma, the plasma which we have on the sun. So it's on top of the pyramid, while low temperature plasma, they occupy, for example, neon lights. This is kind of regions where we basically our operating kind of target for plasma. So it's a bit temperatures about 10 million, maybe 100 million Kelvin, and density, of course, much less than solid state density, and it's a level of 10 to the 13 inverse cubic centimeter, or maybe less. I don't want to to spend too much time to explain you about nanomaterials, but I just showing you with figures to demonstrate nanomaterials which we're working in a lab. So we synthesize carbon nanotubes, boron nitride nanotubes, graphene sheets. Also, we working on hybrid boron carbon nitride nanomaterials, and their examples are here. And some of these examples are from our experiments, and I will show you in brief how they synthesize. We don't synthesize these nanoparticles on surface. It's not like plasma-assisted CVD or CVD. So we synthesize powder. So basically in gas phase, on flight, we synthesize powder particles, flakes, aerosols, and all we do it in arc environments. And this is exactly how Sumio Yajima discovered these carbon nanotubes in 1991, and using simple DC discharge. So you have a plus, it's an anode, you have minus, it's a cathode, you have some distance between electrodes. This is really practical side dimensions, and this is how it works. This is a image taken, filtered image taken with 500 frames per second. You can see arc is between these two electrodes. And while one of the electrodes, which is anode ablate, produce, in this particular case, carbon feedstock. If you add metal catalyst particles, for example, iron or more complex multiple metals catalysts, so you can actually be lucky to grow carbon nanotubes. Usually in these arcs, you grow single wall tubes in the volume as a powder, and they can be semiconducting or metallic. These tubes are short, but they have minimum defects, probably because of high temperature synthesis, which we use. Arcs are scalable, industrial, but there is plenty of drawbacks, such as purity of the product. You need to clean it. Synthesis control is very poor, and limited synthesis limited mostly to short tubes. Of course, all these kind of limitations are driving research, and we want to understand how they grow, because essentially since 1990, a lot of phenomenological models were put forward, but really a model which would be a multi-phase physics coming from ablation to synthesis, whatever it's a vapor, liquid, solid model or something else, or growing tubes, capped or uncapped, it's all remained mostly empirical. And so what we're trying to do is to put diagnostics forward and validate computational codes. And this is what we do at PPPL. So this is a suite of diagnostics which we have in the lab. And these are mostly optical diagnostics which we use for these characterization experiments. It's we involve, of course, we invoke passive spectroscopy and also active spectroscopy, such as laser-based diagnostics, and all for characterization of both gas phase in plasma and nanoparticles. Only by kind of combining all three, we basically can really develop some predictive modeling capabilities, which is the holy grail for us. So this is an example of what we did for carbon, a simple carbon arc experiment. So again, on the left, you can see image of the carbon arc. And on the right, you can see distribution of different plasma species, starting from plasma density, C2 carbon, as well as particles, red curves, form with respect to the center of the arc. And based on this, and so this is temperature, this is particle diameter on the right, plasma density, density of C2, which is a feedstock for carbon nanotubes. And this is carbon feedstock for nanotubes grow. And this is a carbon nanotubes. And you can see applying all these diagnostics in principle, backed by modeling, you can actually see how nanotubes form in such harsh environments, such as arc. And by the way, I forgot to mention with arc operate usually at atmospheric pressure, helium gas or relevant gas, or maybe other inert gases. So this is another example how we apply integrated modeling experimental approach. This is just to prove you that our models not just for making nice images, but also you can see on the left comparison between measurements of the C2 distribution at the top plot and simulations on the bottom plot. And pretty much you can see that with respect to the two electrodes, there is a bubble. We call it carbon bubble form. Basically, the point is that inside, at the center of the arc, you have a very hot arc core where no molecules survive, while molecules form at arc periphery where temperature of the arc become to be colder. And this is the image on the right, combine not only a bubble, which I just showed you before, but also particles form. This is red curve, red clouds on the right, formation of the particles, and there is some models applied. I don't want to go to details. You can look at our publications and understand, but the point is that you can actually predict formation and synthesis information. It's possible. It's just required effort. Just briefly, passive optical emission spectroscopy. It's a passive spectroscopy which you're measuring emission lines, intensity of excited molecular atomic species. We also use active laser-induced fluorescent spectroscopy, which allows you also to measure chemical composition of the plasmas, but also in addition to that, you can actually quantify measurements and also to have a spatially resolved and temporally resolved measurements. And principle is you use laser to resonantly excite specific transitions for atoms, molecules, and even ions to high electronic states, and when fluorescent emission will occur when excited space relax to lower energy state. And so these measurements also, in addition to densities, can give you knowledge about temperature of species and also velocities if there is a flow. For particle measurements, we use the laser-induced incandescence diagnostics, which are very commonly for combustion community, but we applied it for measurements of nanoparticles. So you have a laser beam coming through the arc. It's heating up particles which in volume, and then with either PMT or ICCD, you observe how particles cool down. And based on a model which back up laser-induced condensed signal variations measured, you can actually extract how intensity of the signal connected to the size of the particles. This is example how it's done. For example, if you want to get 2D image using LII of particles. So this is two electrodes, cathode, anode, and this is the particles on the periphery. And so depending how you make your laser beam form it, and then you use ICCD to capture such images. So it's basically powerful diagnostics. However, ARC is, and I showed you it, the first image is notoriously unstable. So look at what's happening. This is actually example of boron, ARC for the synthesis of boron nanotubes. On top you have tungsten cathode, at the bottom you have boron anode, and again boron evaporated. Look at what's happening. So it's a beautiful subject for studying of physics and science and material. Probably science is not, maybe also, but not really a good subject for diagnostics. But this is a way how you can produce almost selectively single-wall boron nitride nanotubes. And this is examples of such tubes and the evaluation of materials. And so we need to deal with that. So these are the key challenges in my opinion, for applications of laser diagnostics for such harsh environments as synthesis of powder in very scalable but very challenging arc synthesis methods. So first, measurement sensitivity of these diagnostics limited, usually not less than 10 to the 8 inverse cubic centimeter. And it's partially associated with hardware limitations, partially it's associated with conceptual ideas put forward in interpretation of the results. For example, it's very hard to measure species which are not spherical, because in all our interpretation of the data, we assume the particles are spherical, but nanotubes by definition not spherical. Also, there is a solutions, of course, for that. For example, to use more better, high sensitivity diagnostics, such as, for example, coherent relay Brillouin scattering diagnostics, which we developed and implemented at PVL in the past. And this is one of the way, but probably there is also other methods of doing such measurements. Also, we have for example, in the case of arcs, and honestly, in the case of plasma torches as well, doesn't matter if it's DC arc or it's a microwave torch, or it's always unstable. They can be sporadically unstable and introduce oscillations in the synthesis region, create unstable flow of the nanoparticles and the mixing up size distribution. And so it's all very hard to interpret it, diagnostic output to put in basically in a precise picture. So therefore, we're usually averaging everything in time and in space. And so also large particle flakes and droplets form in the reactor, obscuring laser beam signal collection. It doesn't matter that lasers can be nanosecond and particles flying, within a second. It's continuous flow. It's always obscuring. So there is different ideas to put forward, but not all these ideas are working properly. So we try to. So one of the kind of solution is actually to create stable environments for synthesis, and this is example of arc for synthesis of carbon nanotubes, again single volt nanotubes, where instead of evaporation of graphite as a carbon feedstock, we're running arc between two electrodes. One is a tungsten, which is not melted, it's a cathode, and one is an anode, which is can be made from iron. And it's all run in methane environment. And so carbon feedstock is by pyrolytic and maybe catalytic in some cases, decomposition of the methane, while metal nanoparticles as a catalyst for growth of nanotubes are from evaporation of the metal anode. And so you basically, the arc is much more stable. It's a very, remind you arc, for example, for welding arc or something similar to that. And so this method basically allows you to achieve more stable operation, as a result, more kind of reliable measurements. However, what we want to know, for example, one of the key parameters to know ablation rate of the metal in order to understand yield which you can achieve. And so because metal evaporate, then condense, forming nanoparticles, which act as a seed for growth of carbon nanotubes from decomposed methane products. And so in order to know ablation rate, it's one thing is to measure weight of the electrodes, and now is you need to know temperature of the evaporated surface. And unfortunately, when you have two metal electrodes and one of them is molten, and you want to measure temperature of molten electrode, which is nearby in our electrode, the problem is basically reflection of the light from the top electrode, which you don't want to evaporate, on the electrode which you do want to evaporate. And as a result, it's obscuring temperature measurements. Also, since you're acting is in a carbon environment, carbon can actually get diffuse, and you can basically get, you're starting with pure iron and getting with carbon steel, and so emissivity constantly changes. So what we, as a solution, we found the two things. First, we're using two-color pyrometry, which allow us basically to mitigate effects of the changes of emissivity. And then second is we're using shutter, which when we want to measure arc, and this is the trajectory of the shutter, we basically kind of prevent mirrored image on a molten electrode from the top electrode. And this is how it's done. And then we can measure temperature of real temperature of the molten surface. Then we can apply it to the formula for evaporation and or models for evaporation, and basically predict our evaporating capabilities. This is what we implemented, and it works well. So basically, for every problem, there is a hope to find solution, and we're finding them. Also, quite difficult in some cases, in some real reactors, especially industrial reactors, to give access for laser diagnostics. And laser diagnostics are usually likes to have 2 or 3 viewports for implementation. And one viewport for laser in our viewport 90-degree for collection optics, and one also sometimes viewport for beam dump. And it's not always possible in such environments. So what we come up is we just basically took some implementations from what you developed in material science, such as confocal diagnostics. And these allow us basically to measure properties of the plasmas even when you have a limited access. So basically, we need just one viewport to get information on a species, and this solution, which very well known for material science and biology, actually surprisingly is not so much popular in plasma experiments, probably because in plasma experiments you usually don't have problem with access, optical access, but in reactors, industrial reactors and synthesis reactors, it's basically always problem. So anyway, so this is my last slide. So limited diagnostics access, we can solve it by, for example, confocal approach. And for temperature, and it's more specific, for temperature measurements of the operating surface, we can find solution on 2-color perimetry with shutters. And so basically, this is my acknowledgement. And what I also would like to mention is that all these diagnostics available, we are very welcome people to come to us, contact me. We have the same procedure. It's for user proposals, which just previous speaker described. We have some call, which is coming in October this month. And there is an evaluation of the user projects. And if we can handle these user projects and provide service, then you're getting our expertise and our diagnostics for free of charge, because it's supported by our Department of Energy, Office of Science, Basic Energy Science, and Fusion Energy Science. Thank you very much.
Thank you, Dr. Reitzes. This is very interesting. If anybody has any questions, please put them in the Q&A section. But I do have a question just kind of to start. So as far as with looking at kind of the overall stability of your plasma and like the regions between the electrodes, in one example, you had a feed gas as a carbon source, which was the methane. But I just wonder how much interference or how much effort goes into figuring out what kind of like pressures, as far as using like argon and ambient pressure or different inert gases, goes into any kind of interference that you might see from your detection suite.
Yeah, very good question. Thank you. Basically, we use, for example, laser-induced fluorescent diagnostics is a resonant diagnostic. So when we select wavelengths to excite species, we're targeting specific species, which it's not always well-documented transitions for LIF. We actually just recently made a big review of all known, we tried to capture all known transitions, and we found maybe 150 or so. So it's really like not big number, and it's covering not only synthesis of particles, but it's for other applications. So unfortunately, there is not really a solid database for LF transitions. But fortunately, for all carbon, hydrocarbon species, for majority of them, you can always find transitions which can be representative of the process. This is basically just fortunately, and possibly because combustion community spend a lot of time using LIF as a tool. And so these resonant transitions, of course, will not be problematic to use. Much more complicated for other materials. There are different things may happen. For example, some transitions may, especially fluorescent with collections transitions, may overlap. So you resonantly excite one species, but you may actually get fluorescent signal obscure or overlap with another signal. Things like that happen, especially in molecular regions. So therefore, it's needs to be very carefully checked, rechecked. Whatever you're measuring species which you targeted, or you're measuring something which you didn't expect. And so in many cases, it's not so difficult to do. But for example, when you're using such diagnostic tool for microelectronics processing, it's much harder. It's much harder. And we had the cases when, we thought that it will be oxygen, and it's actually, I mean, special oxygen species, and it was something else, silicon oxide, for example. And need to be careful. So basically, you need to be confident. Now, for two-color pyrometry, most important was not to get obscuring, not to interference, for example, with to be away from emission lines, from argon lines, because it was in argon, or from nitrogen lines. So you need to carefully select the wavelengths to operate. So basically, careful considerations and not just taking data as it is. Unfortunately, it's not plug and play.
That's fair. And I guess in this last little minute, I just want to ask, once you've produced the samples, is there kind of a suite of things, say for carbon nanotubes, you're getting short nanotubes, you might be getting fullerenes, I don't know what kind of, substances. Is there something that you're using to look at or characterize, the distributions of morphologies of species you're producing?
Yes, PPPL doesn't have material science facilities, but I mean, we have some surface science lab, but not heavily equipped with material science facilities. So we're going to Princeton University Imaging Center, where we have access to TEM, SEM, Raman, XRD, XPS, whatever is needed for measurement. So of course, it's 4 miles away, so we need to travel. Well, we're using boxes and, argon pressurized, trying, if the problem is oxidation or getting, water molecules somehow inside. So we're basically trying to protect us. So this is how we do. But we have a shuttle, so it can be done.
Yeah. Great. Well, this was really awesome. Definitely a wild application. There is a question in the chat box, but if you could maybe try and answer that offline so that we can get Dr. Abul Hassani on.
Sure.
I want to thank you again so much for your talk.
Of course.
Very
Thank you very much. Thank
Yep.
you very much. And congratulations with the Nanotechnology Day.
Oh, yeah.
Big.
Okay, take it over.
Okay. Can you see my screen in the presentation mode?
Yep.
Great. Well, hello, everyone. Thank you for the opportunity to talk about some of the work we've been doing in my lab over the last 7-8 years to accelerate the way we search for new materials and we develop new nanomaterials, we characterize them, and then we also manufacture them at scale. So today I'm going to give you a brief overview of how we envision in my group to integrate human prior knowledge and expertise with robotics and lab automation and AI to accelerate navigation through very large chemical space and material design space of advanced functional nanomaterials. So when we are conventionally looking for materials, we are typically searching a very large, what I call a material universe. We don't have a map of this universe, so most of the time we're just blindly searching through this space using Edisonian trial and error-based methods. So this is why this is 50% of the problem of why our material discovery efforts are resource and material intensive. The other part of the problem is the way we conventionally approach material discovery. So we typically send our highly trained scientists in the lab. They spend 70-80% of their time just doing repetitive tasks, maybe pipetting, preparing samples, running reactions, characterizing the products. And at the end of the day, they've done maybe 1, 10, 20 experiments, and they go back to the computer, look at the data, and use their intuition to decide what is the next experiment to do. So this is our conventional closed loop science, here, mainly relying on the human knowledge and human manpower to do experiments. So by nature, this is inherently slow and resource and material intensive. So when you look at this picture, there's a lot of room for improvement to take our human scientists out of the lab and not out of the closed loop of science and material discovery, just bringing them out of the lab so we can maximize the use of their brain instead of just their hands. So we can leverage the recent advancements in robotics and lab automation to automate the experimental workflow of material synthesis, nanomaterial synthesis, solution phase, solid state synthesis. We can bring robotics, lab automation in the lab, so we can have this end-to-end automation of our experimental workflow. And then in order to decide what experiments to do next, we can leverage all the recent advancements in AI to model our reactions and then use high-dimensional space modeling with AI agents to decide what is the next experiment to do. So we use AI agents both for experimental planning and optimization. So when you integrate robotics lab automation with AI agents, you get what we call a self-driving lab. Now, what are some promises and opportunities that self-driving labs provide? This is like an intelligent robotic co-pilot that bridges the AI co-pilot in the digital world to the physical world. And it has the potential to accelerate discovery of new materials and molecules and even sustainable ways of manufacturing these materials at a scale by 100 to 1,000 times compared to the conventional methods we've been doing and using in chemistry and material science labs over the last century. And by nature, it reduces the carbon footprint of discovery. If we can go from 10 plus years of discovering a new material for renewable energy and sustainability applications, if we can go down to a few months or even weeks, we can significantly reduce the carbon footprint of material discovery. It can also reduce the time from lab to market. So in a self-driving lab, you start with the human-defined scientific problem, and then you can leverage virtual screening tools, machine learning-guided DFT, for example, to down-select some potential candidates for a specific problem that you're looking for. But those predictions are still in the digital world. We call those hallucination of your AI agent, for example. And then the self-driving lab bridges that gap between that digital prediction to the physical world. And it uses robotics and lab automation and AI-guided orchestration of these robotic modules to test the hypothesis and initial predictions by the AI agent. And then it refines the hypothesis, and it either comes up with a new material or it can verify that the material predicted by your AI agent is synthesizable and then optimize the material in a closed loop format very, very quickly. And you get a lot of advantages through this self-driving lab exploration of your material design space. But at the end of the day, the most important value proposition of these self-driving labs is the reduced time to solution by 100 to 1,000 times. Then the next question is, how can we design an ideal autonomous lab? So there's a lot of things that you have to consider. Of course, you should not go in the lab and start automating everything you find in your lab. That's the worst way of building an autonomous lab. You have to start thinking, well, what are the most challenging bottlenecks of your experimental workflow? Let's just start with the bottlenecks, and let's just start automating and that is specific bottleneck, increasing the reliability and reproducibility of that specific bottleneck. Your bottleneck could be the synthesis, it could be sample preparation or characterization. First, understand what is that bottleneck. And then think about material efficiency. At the end of the day, if you're doing discovery or optimization, you're going to need to do hundreds of experiments, sometimes thousands of experiments. So once you're designing an autonomous lab, you have to consider that material efficiency. You want to miniaturize and minimize chemical consumption and waste generation. Then the precision and reproducibility of your automation becomes extremely important because that's going to directly define what is the noise of the experimental data that you're generating and feeding to your AI agent to train your model. And then all the decisions made with your AI agent, by your AI agent, is going to be tied with the precision and reproducibility of the data that you're feeding there to your AI agent for training. And then how to do reliable automation, when do you incorporate human knowledge, and so on. At the end of the day, what we want to have is a big, reliable experimental data so we can match the experimental data generation throughput with our AI agent data needs so we can continuously train and revise and refine our AI agents so that they can do better and better predictions. Now, thinking about the big, reliable experimental data, the next question is, what kind of reactor do you want to use to run your material synthesis? So if you're doing any sort of solution phase synthesis, typically the gold standard is to use a batch reactor that you can put all of your precursors into an autoclave or round bottom flask, and then you can just heat it up, run your reaction, and then sample at the end of the reaction or during the synthesis. But batch reactors by nature provide a lot of limitations. So first of all, you end up with wasting a lot of your reagents. Sometimes these are expensive and toxic chemicals, and then you end up wasting a lot of your solvent. And then you have to wait a lot. You waste a lot of time during the heat up and cool down when you have to do high temperature synthesis. And you're limited in terms of the processing parameters. And you always have this difficulty of integration with in situ online characterization tools to monitor the experiment or the synthesis of your nanomaterial during the reaction. So in order to address these limitations of batch reactors in synthesizing nanomaterials, especially colloidal nanomaterials, in my group, we go from batch to flow reactors, and we synthesize these nanomaterials, colloidal nanomaterials, in a microfluidic reactor. Microfluidics has been around for more than 30 years, and most of you at least have heard of the word microfluidics, but the most important reason that we use microfluidics to synthesize our colloidal nanomaterials is because of their enhanced heat and mass transfer rates and photon flux absorption. So if we have a process that is heat or mass transfer limited in batch reactors and might take hours or sometimes days to run that reaction, we can reduce that reaction time to in the order of a few minutes to run it in a flow reactor. And we can reduce our chemical consumption by a few orders of magnitude, and we can readily integrate these microfluidic reactors with in situ online characterization tools. We can do in situ spectroscopy or online mass spec and so on. So that miniaturization, reduction of the chemical consumption, and acceleration of kinetics, and the ease of integration with in situ online characterization tools are the most important unique attributes of microfluidic reactors. And those are the main motivations in my group that we use these microfluidic reactors for synthesizing nanomaterials. So in my group, we basically develop our bespoke flow reactors to synthesize a wide array of nanomaterials. And then we use robotics and lab automation to automatically prepare our precursors. That's liquid handling and solid handling, for example, under an inert environment, so that we can automatically and continuously prepare different starting precursors of nanomaterials selected by our AI agent. We develop our own bespoke in situ characterization tools, spectroscopy, and then we integrate these in situ characterization tools with our flow reactors to automatically characterize the product leaving the reactor. And then we use AI agents to orchestrate and operate the overall end-to-end automation workflow to test or to rapidly answer the problem defined by the human user. And then we use these foundational technology or autonomous labs to accelerate discovery of new nanomaterials in the colloidal nanoscience world. We also use these self-driving labs to accelerate discovery of catalysts and new processes for homogeneous catalysis. And then the third research cluster in my group, we use all the data models that we develop in nanoscience and catalysis applications to better understand the underlying mechanisms of the processes that we study in the nanoscience and catalysis work. So for today, I'm just going to focus on some examples of the nanoscience applications. As I said, we have been working in this field for the past 8 years. These are some examples of some of the self-driving labs that we have developed over the last few years to accelerate discovery of advanced functional materials. So I mentioned robotics. So this is an example of how we use robotics in my lab to automatically prepare different precursors of nanomaterials or even catalysis applications. So we do solid dispensing and liquid dispensing automatically with robots under an inert environment. So this is inside a glove box under a nitrogen environment. We have different solid dispensing containers, different liquid stock solutions, solvents, and so on. So we can automatically prepare the precursors, the starting precursors of our reactions. And we can do even initial solubility testing of the precursors to make sure everything is completely soluble. And then we use robotics also for sample transfer. Let's say you synthesize your nanomaterials and you have to do some ex situ characterization, and your characterization tool cannot be integrated with your reactors. You can use robotics to automatically transfer your samples between different robotic modules. So we use both mobile robots and stationary robots to transfer our samples between formulation, synthesis, and characterization module. But as I mentioned, we use microfluidics to run the reactions and synthesize these nanomaterials. So these are two examples of flow reactors synthesizing colloidal nanomaterials into blue droplets, flowing in a tube. The inner diameter of these microreactors or tubes is in the order of a few hundred microns. So as I said for today, I'm only going to talk about the nanoscience application. So the test bed for self-driving labs in the nanoscience trust in my group is colloidal semiconductor nanocrystals, or known as quantum dots. Quantum dots got a Nobel Prize in Chemistry in 2023, and they have a variety of applications ranging from devices to solar cells, to biomedical imaging, and even quantum information science. But some of the unique attributes of these quantum dots is, first of all, their solution phase synthesized, and by tuning their composition size or surface chemistry, you can really tune their optoelectronic properties and optical properties. For example, here is an example of the same class of quantum dots with different composition, and you can see their emission color is really tunable from blue to red. And they have very narrow emission line widths, and they have very high quantum yield, which is the ratio of the photons they emit over the ratio of photons they absorb. Because of these unique attributes, they are great candidates, as I said, for device applications like TV displays, LEDs, photodetectors, solar cells, and even quantum information science. So in order to accelerate discovery and development of quantum dots, we've been designing and developing multiple generations of self-driving labs over the last 8 years in my group. In terms of the hardware, we focus on the modularity and the versatility of the formulation, synthesis, and characterization modules of these automated platforms to automatically synthesize quantum dots. So we have a precursor formulation module that we can use our automatically prepared precursors with our robotic platforms to continuously feed the precursors into our reactor and then form these very small droplets in the order of half a microliter to 1 or 2 microliter per droplet. And then these precursors that are mixed, they're continuously flowing along the flow reactor. And this is where the nucleation growth of these nanocrystals will start happening at a specific temperature for a given reaction time. At the end of the reactor, we do in situ characterization, where we can do in situ UV-vis, near-infrared absorption, and photoluminescence spectroscopy to characterize the optical properties of these in-flow-synthesized quantum dots. And just from the absorption of photoluminescence spectra data, you can extract a lot of information about the size, concentration, band gap, the size distribution, and the quality of these quantum dots that are synthesized in flow. So here's an example of our in situ characterization module where we are doing in situ spectroscopy. We have 2 different light sources. One is a broadband light source on the left, and then one is a high power LED on the top. And then we have a fiber coupler spectrometer. By toggling between these 2 light sources, we can automatically record the absorption and photoluminescence spectra of these quantum dots in the blue droplets that are synthesized in our flow reactor. And this is another example of our bespoke in situ characterization module. In this case, the module is actually moving along the reactor because we don't want to change the mixing of the precursors inside these droplets. So this flow cell is automatically moving along the reactor, and it's recording the optical spectra of these quantum dots synthesizing these droplets at different positions along the reactor. Each position corresponds to a different reaction time. In this case, we can have acquisition time scales of milliseconds. And then with just the automated reactor and then in situ characterization module that I showed you, we can visualize these reactions of quantum dots. For example, this is a halide exchange reaction of metal halide perovskite nanocrystals going from cesium lead bromide nanocrystals to cesium lead iodide and chloride by just doing a halide exchange reaction inside these droplets. You can see the absorption photoluminescence spectra at the bottom left, and you can see the amount of data they can generate just doing in situ spectroscopy. spectroscopy. Here's another example of in situ spectroscopy and flow synthesis. This is for metal cation doping of metal halide perovskite nanocrystals. This is manganese dope cesium lead chloride nanocrystals. And this is a very fast reaction in the order of 2 seconds. But what I want to highlight here again is at the bottom right, you can see the amount of data we can generate with in situ spectroscopy to visualize the reaction, monitor the reaction, and provide in situ experimental data that you can use to train your AI agent to decide what should be the next experiment to run. Now, in addition to the synthesis, formulation and synthesis of these quantum dots, we've also developed modules that allows us to very rapidly study the quality of these quantum dots when they're exposed to high energy photons. This is the UV stability of the nanocrystals. So with this reactor that's coupled to high power collimated UV light source, we can basically rapidly, within 10 minutes, study the photodegradation of these quantum dots. So what I've shown you so far is that with an automated flow reactor, we can automatically control the starting precursor, their concentration, their mixing. We can also control the synthesis with a specific reaction time and temperature. And then we can do in situ spectroscopy to characterize the optical properties or structural information of these nanocrystals that leave the flow reactor. Then we can use all the data that we generate with our flow reactors to train a predictive model, a machine learning model, for example, a Gaussian process regression or an ensemble neural net, and use the uncertainty quantification of your model to guide the decision-making of what should be the next experiment. This is the automated decision-making under uncertainty within, for example, a Bayesian optimization framework, so that you can automatically decide what should be the next experiment and then send it to your automated platform to run the next experiment. And that decision-making is defined based on the objective that you're looking for. The objective could be, I'm looking for a specific band gap, find the nanomaterial that has a specific band gap. That's a single objective optimization, or you can have multi-objective optimization of minimizing the emission line width or size distribution of the nanocrystals for a specific band gap. Now, in order to study what is the best way of making those decisions with the AI agent of your self-driving lab, we, in the past few years, we have developed multiple digital twins of our flow reactors using our in-house generated data. Basically, we've used thousands of experimental data we have generated in the lab to train a machine learning model that replicates the exact operation of our physical platform. So in this case, we can put our physical platform aside and use that digital twin, digital replicate of our experimental platform to benchmark and test different parameters of the AI agent of our self-driving lab. So after we fine-tune all of those parameters, or after we find out what is the best AI agent of self-driving lab, then we integrate that with our automated solution so we can autonomously search for the synthetic route of any specific nanomaterial that we are looking for. So this is our first self-driving lab that we built. This was 5 years ago. We call this Artificial Chemist, and we showed that with this autonomous experimentation platform, within only 90 minutes, we could discover the synthetic route of the highest quality quantum dot for a specific given band gap. And then you can also reconfigure the operation, go from the R&D, discovery and optimization to continuous manufacturing at a scale that is relevant to device applications. Then later on, we did the second generation of this artificial chemist that we could do multi-step synthesis. The first reactor is synthesizing, for example, cesium lead bromide nanocrystal. The second one is doing a halide exchange with a halide salt and a specific ligands. In this case, with 9 different input parameters and 3 outputs and active learning guided experimentation, we showed that within 40 minutes of autonomous experimentation, we could discover the synthetic route of the highest quality metal halide perovskite quantum dots for any specific band gap. And most recently, we wanted to see if we can push the limits of our self-driving labs and see if we can discover the best-in-class quantum dot. For in this application, we focus on multi-cation dope metal halide perovskite quantum dots. This is manganese and terbium dope, cesium lead chloride. Before this work, over the last 5-6 years of academic literature, the highest quality of these multi-cation dope metal halide perovskite quantum dots was found to be 138%. The theoretical limit is 200%. So with this self-driving lab that we built, it took us like 3 years to build it. Within just 1 day of autonomous experimentation, we showed that we can find the best-in-class multi-cation dope metal halide perovskite quantum dots for applications in smart windows, luminescent solar concentrators, and even solar cells with a total quantum yield of 158%. So that's just one day of autonomous experimentation, combining human knowledge, that's a prior knowledge of the precursor chemistry, with reactor engineering, that's the automation of the reactor, and the AI that models the reaction and decides what should be the next experiment. So this is a good example of how we can integrate human knowledge with AI and robotics to push the boundaries of what is possible in nanotechnology and nanoscience. So in this case, the reaction was a high temperature sensitive, 300 degrees Celsius, and we had 11 different inputs and 3 outputs. So a very large experimental designer space, but this self-driving lab was able to navigate that high-dimensional designer space very rapidly and discover that best-in-class quantum dots. So this is a video of showing the reactor in operation. This is high temperature, 300 degrees Celsius. That's why you can't see the reactor. It's thermally insulated, but you see the droplets leaving the reactor. This is under UV. You can see the emission of these multi-cation doped metal halide perovskite quantum dots leaving the reactor. And this is where we do in situ spectroscopy, the character optical properties of these quantum dots. And we looked at different decision-making policies to make sure that we're using the most optimal decision-making policy for the AI agent of our self-driving lab. And after we discovered that best-in-class quantum dot, we showed that we can automatically transition from discovery mode to continuous manufacturing and continuously manufacture. This is a 5-hour continuous manufacturing of the best-in-class multi-cation doped quantum dots without losing the quality of these quantum dots. So we could produce a few grams of these quantum dots that you can make multiple devices out of this. So for the sake of time, I'm going to skip the last example and jump into what is the future of self-driving labs. So what I showed you was just a glimpse of what is possible with the self-driving labs, integration of human knowledge, AI, and robotics and lab automation. So moving forward, we can maximize the possibility and opportunities that these self-driving labs offer by working on standardization and basically democratization of these very powerful research acceleration tools and distribution of these self-driving labs within every chemistry material science lab and even facilities at every institution. But in order to do this, we need to start thinking about the standardization of the hardware and the digital side of these self-driving labs. We have to make sure that data that we generate is reliable and reproducible, so we can augment data and fuse the data across different autonomous labs so we can further accelerate discovery of new materials or molecules. So with that, I hope I was able to convince you that autonomous labs are great robotic co-pilots to help us navigate high-dimensional spaces of new, emerging, and complex advanced functional materials, and they can help us reduce the time and scale gap in material discovery of 100 to 1,000 times. So at the end, I want to thank all my group members who actually did all the work I presented today. I didn't do any of those experiments. I want to thank all of our funding sources, especially NSF, and our sponsors, industrial sponsors. And I want to thank my collaborators, Chris Reyes and Yu Chen. I want to thank you all for listening. I'll be happy to take any questions.
Well, that was really impressive. That was definitely really interesting. I think a lot of people are really interested in this space of going towards kind of full digital twins for setups. And I wonder a little bit about the kind of training process, especially for things like let's say the solvent selection or something, like when you're choosing your biphases or the types of surfactants or whatever else is going into these, how do those kind of small kind of basic chemical questions translate to things like the performance of, say, the droplet formation or the stability of just the microfluidic reactor setup?
Excellent question. So as I briefly mentioned in the early part of the talk, we we use robotics to automatically first explore the solubility, viscosity of our starting precursors. Now, your question had multiple angles. So the ligand, for example, is one of the most important parameters when you're doing any colloidal nanomaterial synthesis. Selection of the ligand and sterics of the ligand, all the properties of the ligand, extremely important. And that's not well understood in colloidal nanoscience. We know we have some general understanding of you need an acid and organic acid, organic base. You need to have a surface neutral ligand coverage at the end. But what is the role of the ligand structure on controlling the morphology and optical properties of your nanomaterials? That is not well understood. So the way we approach that with machine learning assisted experimentation is by first starting with just treating different ligands as different discrete parameters. I have a library of 20 different ligands, and I want to find out how each of these ligands map to the morphology and optical properties of one nanomaterial. But then in the next step, once you build that infrastructure, the next step, you can start incorporating different molecular descriptors and information of your ligands into your machine learning model so that you can map, for example, the angle, the molecular properties, the different structural information of your surface of ligands into the properties and morphology of your nanocrystals. And once we accomplish that, then we can use that model to help us better understand the key role of molecular properties of the ligands on controlling the morphology and the optical properties of the nanocrystals. And then we can use that to design new ligands to give us the highest performing nanocrystal or nanomaterial you're looking for with the best stability and so on. But it takes us some time to get there. So we go one step at a time. Right now, we are at the stage that we can explore that discrete continuous space, and we're working on incorporating those descriptors into our predictive models.
Well, I want to thank you again for coming to give your talk. This was really wonderful. I want to thank everybody who joined today. And I think we're going to wrap up. Do something for Nano Day. I will be looking forward to seeing you all for the next webinar. And Dr. Abel Hassani, I want to thank you again. This is really interesting.
Thank you.
Thank you, everybody, for showing up today, and have the great rest of your day.